Hello, welcome to the next in our mini little course on Introduction to MPC. Last time we looked at Shamir secret sharing in a lot of detail, so what I do is in this week we're going to kind of expand this a bit more, so it's probably worth your while going back and having a look at the previous mini little lecture, and that will then form the basis of what we're going to do. Okay, so what we're going to do today is look at general linear secret sharing schemes, of which the Shamir example is the classic example that you see to start with, but we want to generalize it a bit more. The way we're going to generalize the Shamir example is in two ways. First way, we're going to look at what are called Q2 access structures. Now these are a bit like Shamir or threshold structures when t is less than n over 2. In particular, the union of no two maximally unqualified sets is the whole set. So imagine when we had n equals 3 and t equals 1, then what we had is that the maximally unqualified sets of parties is the individual parties. So we've got party 1 or party 2 or party 3, and a union of no two of those is the whole set. Okay, so that's what Q2 means. Full threshold is the case when we have n parties and we need all n of them to come together. So it's kind of the most extreme example of a threshold system. So we can look at both Q2 and full threshold because they're the ones that are really interesting in applications. And in both of these cases, we want to generalize the ability we had last time to open shares and check that they are correct, i.e. that they haven't been tampered with. So that's what we're really interested in, is defining not being tampered with. Okay. So the first thing we're going to do is actually generalize what we talked about with Shamir. And this is what's called a linear secret sharing scheme. So a linear secret sharing scheme is basically given by a matrix M and a vector V. So there is this matrix M, which has m rows and d columns. The vector has d entries in it, and then there's this map which maps the columns, remember there's m of them, to the parties, and there's n parties. So because you've got a three-party scheme, n is 3. Okay, so to share a value in a linear secret sharing scheme, which is defined by this m, v, and chi thing, what we do is we take the secret that we want to share, s, and then you pick a randomization vector k in the finite field, d elements of the finite field, such that the dot product of this vector v times k is equal to s. And then to define the sharing, what we do is we take the matrix M and we multiply it by k here. Okay, so that gives us the set of shares, but there's m of these shares, but we've got n parties and m is bigger than n. So what shares do we give to which parties? Well, which shares we give to which parties is defined by the function chi. Okay, so that's kind of what it is. And this is what's called, in theory, what's called a monotone span program. But we're just going to think of it as a linear secret sharing scheme. Okay, so that's how we define the sharing. How do we actually reconstruct? Okay, when we've got the shares, how do we get the secret back? Okay, so a set of parties can recover the secret if the span of the rows are, of the matrix, the rows in the matrix that they control, contain V. In other words, if they control, if these two parties say control rows 1, 2, 3, 4, 5, then a linear combination of the rows 1, 2, 3, 4, 5 will contain this target vector V. And why is that? Okay, that's because if V is contained in the row span of this submatrix M sub A, then there is a vector XA, there just exists one, such that the target vector V, which is part of this definition we had on the previous slide, is equal to XA times MA. Now, what that means is that the shares that the parties have, which we can think of as MA times K, which is just their set of shares corresponding to the rows that they have. So M sub A is just the matrix with their rows in only. Then, well, if we take the dot product of this vector xa with sa, then what we get is we get the secret out just by elementary linear algebra. So we can think of this xa vector here as the recombination vector. It is a vector which allows us to take a qualified set of shares SA and recombine them to get the secret S. So that's how we do recombination. And it turns out that over a finite field that if the vector V is not in the span of the rows controlled by the set of parties in A, then the set of parties learn no information at all about the secret. So we have this nice relationship between if V's in the linear span, then you can recover. If V's not in the linear span, then you learn no information whatsoever. So it's exactly what we want from a security point of view. Okay, now the other advantage of this representation of a secret sharing scheme is it allows us to compute, just like we did with Shamir, it allows us to compute arbitrary linear functions of the underlying secrets without any form of communication. And this is trivial from this linear representation. It's a linear representation, we can compute linear functions. This is not surprising, yeah? So, okay, so if you have two shares, which are shared, by that system, because we have two vectors, k and k dash, such that dot product of the target vector times k is equal to s, and the target vector times k dashed is equal to s dashed, then the sharings are given by the matrix times this randomization vector. But then we know trivially that s plus s dash is going to be shared by the sum of the shares, because that's equal to the matrix times the sum of the two randomization vectors. And if we took the sum of the two randomization vectors times the target vector, the dot product would equal to s plus s dash. So we can compute arbitrary sums. We can also compute arbitrary products of a multiplication by a constant. So if we had a constant alpha, we can compute the secret sharing of alpha times s just by multiplying each share by alpha. So that's kind of a really nice. So what that allows us to do is, if we kind of use this notation of square brackets s to denote the fact that the value s is shared under this linear secret sharing scheme, then we can compute arbitrary functions like this. We can take an arbitrary known constant multiplied by sharing of x plus an arbitrary constant multiplied by sharing of y, and then we can add an arbitrary sharing of a known constant on again. So we can compute arbitrary functions like this for free, essentially with the same cost that we would of computing on the values in the clear. Okay, so we've got this general thing of linear secret sharing schemes. It just seems a generalization. Is it useful? Okay, so it's exactly what we had for Shamir. Shamir, we had this matrix which just happened to be, it had as many rows as we had parties. It was n by t plus 1. Okay, so that's where this comes from. The target vector was 1, 0, 0, 0, and we assigned party 1, row 1, party 2, row 2, and party n, row n, which is what the function chi does. So Shamir is a linear secret sharing scheme. So what we've just done is just a generalization of what we did in the previous lecture. Full threshold sharing is also a linear secret sharing scheme. It's also nice and trivial. What we have is that a secret is shared if you just have S1 plus Sn, and you give party 1 S1 and party n Sn, and then they all have to come together to recover the secret. And that is a linear secret sharing scheme because we've got the matrix, which is given by the n by n identity matrix. We have the target vector, which is the all one vector, and we assign party 1 row 1, party 2 row 2, and party n row n. This is exactly the same as in the Shamir case, just different matrix, different, yeah. So we're kind of generalizing here. We can do anything. We've had Shamir, which gives us a threshold structure, and we've got full threshold. So what other access structures can we define? Okay, so an access structure is actually defined by the set of minimally qualified sets, or equivalently the set of maximally unqualified sets. Okay, and for Shamir, the set of maximally unqualified sets are all of size t, and for full threshold, the set of all maximally unqualified sets are of size n minus 1. And what must an access structure be? Well, it's going to be what's called monotonic. In other words, if I add someone to a set, if a set can still recover the secret and I add someone to it, well then that set can still recover the secret. Okay. And you know, so adding someone doesn't make you unqualified, it only makes you more qualified. Okay, so that's what we mean by monotonic. Adding people can only give you more power, can't take power away from you. Okay, so here's another example of a way of doing secret sharing for threshold. So this is what's called replicated secret sharing. So this shows us that we can have different linear secret sharing schemes for the same access structure. We don't necessarily have to have the Shamir for threshold, we could have other ones. So this is a very classic example. So here we want to have 3 parties and we want to share a secret such that 2 of them have to come together to recover the secret. And this is what's called replicated. And what we do is we have this matrix here, which the first 2 rows correspond to party 1's shares. And you see that they have nothing in entry 1. The second, the rows 3 and row 4 correspond to party 2 shares, and they have nothing in the second position here. And rows 5 and 6 correspond to party 3 shares, and there's nothing in position 3 here. And the other positions are just taken up by the identity matrix. Okay, so and then the target vector is 1, 1, 1. Okay. So the idea is it's replicated because if you think about it, party 1 is going to hold this value, is going to hold K2 or S2, but also party 3 is going to hold S2. Party 1 is going to hold S3, and party 2 is going to hold S3. Party 2 is going to hold S1, and party 3 is going to hold S1. So we're replicating the shares, hence the name. So if I hold a share, then someone else is going to hold a share as well. It's going to be replicated elsewhere. That's why it's called replicated. And we could define other access structures as well. So let's imagine this example here. What we've got is we've got 4 parties, and this is like the graph of all possible subsets of 4 parties. Okay, so now let's define an access structure. So first, what we do is we define the set of minimally qualified sets. So let's just, for example, say that we want 1, 2 to be a minimally qualified set. So every set which contains 1, 2 as a subset is going to be qualified. The same for 1, 3, and the same for 2, 3, 4. So this is clearly not a threshold structure, okay? So we're clearly doing something a bit more exciting than just boring threshold structures. Okay, so we've got the minimally qualified sets. Now from those, we can now just add in monotonicity, which says, okay, anything which contains a minimally qualified set must also be qualified. So that adds these sets in here. And also anything that's a subset of a minimally qualified set has to be by definition unqualified, because a subset of a minimally qualified set must be unqualified. Okay, so these sets here are all unqualified. So we've got one set on its own here for which we haven't made a decision yet. So we've got to make a decision. It could either be qualified or unqualified, but it's got to be one or the other. So we're going to make it qualified. Okay, so we've now defined an access structure. Okay, so this is an access structure. Can we define a secret sharing scheme for it? Okay, so what we do now is we define the maximally unqualified sets. Okay, so we've now got those maximally unqualified sets there. So this access structure. Brilliant. Now notice that this is a Q2 access structure because the union of no 2 unqualified sets is the whole set 1, 2, 3, 4. Okay, so 1 plus 2, 3 is missing 4. 2, 3 plus 2, 4 is missing 1, and so on. So we don't have. So there's definitely a Q2 access structure. So it's kind of interesting. We're going to come on a bit later on of why we're interested in Q2, but at the moment just kind of think that every kind of non-full threshold scheme we're looking at is going to be Q2 for a reason. Given that access structure on the previous slides, can we come up with a secret sharing scheme for it? It turns out we can by a general construction which gives us a replicated secret sharing scheme. So what we do is we first start with the set of maximally unqualified sets, which were those 4 sets there. Remember, those were the sets in blue on this slide. Okay. Now what we now do is we take the complement of those sets. So we take these maximally unqualified sets here, and then we take the complement. So the complement of 1 is 2, 3, 4. The complement of 2, 3 is 1, 4. And then what we do is for each of these complements, we define a secret. We share the secret S by having S is a set which is the sum of 4 things for all of the 4 things in the complements of the maximally unqualified sets. Okay, so that's how we do the summation. And then we send the sharing SB, so S234, so this value S234 we give to party 2, to party 3 and party 4. We give S14 to party 1 and party 4. S13 we give to party 1 and party 3. And S12 we give to parties 1 and parties 2. And we call that sharing, the square bracket sharing again. So here we go. So party 1 has S12, S13, S14. Party 2 has S2. And it's kind of clear that if we look at those maximally qualified, the minimally qualified sets, that the minimally qualified sets can recover. So what was a minimally qualified set? Let's go back. Okay, so minimally qualified set was something like party 1 and party 4, say. So let's look at party 1 and party 4. Well, party 1 and party 4. Well, what's party 1 missing? Well, party 1's missing the share 2, 3, 4. So if party 1 and party 4 can get together, they will both of them have all of the 4 shares needed to recover S. It's just as simple as that. It's really kind of a cute way for any access structure of defining a secret sharing scheme. So replicated is really important if you want general access structures. So what's the underlying linear secret sharing scheme? Well, it's this. It's party 1 is in control of the first three rows in the matrix. Party 2 is the next 2, party 3 the next 2, and party 4 the next 2. And the target vector is 1, 1, 1 because the sharing was a sum like that. And then we just map this mapping to the matrix and we get that. And if you did the same for the replicated secret sharing of the threshold structure, you'd get the matrix we had there. So that's a kind of nice example. Now what we come is to how do we open Q2 sharings. Okay, so we've got similar problems that we have for Shamir. So if we receive n shares from someone and one of those people is an adversary and has introduced an error, we can detect this. Okay, and the way we did that is we detected it via a parity check matrix. Okay, so if we do not report, if the parity check matrix gives us the correct output, it gives us, there is no error, then what we do is that we can recover the secret and continue. And if the parity check matrix says that there is an error, then we abort. Okay. Now the parity check matrix only has this property if the underlying secret sharing scheme was Q2. So Q2 is really important here because this allows us to do error detection. Okay. Okay, now we've got the issue is that suppose that we didn't receive the shares from from everybody, but we only received them from a qualified set. So in that previous example, suppose I'm party 1 and I just received the shares from party 4. Okay, so we want to reduce the amount of communication going on. So party 1 only gets data from party 4. So I don't know whether party 4's cheated. So how am I going to what I now do is I need to work out whether party 4's cheating or whether party 2 or 3 are cheating or whether everyone's being honest. Okay. So what I now do is I reconstruct the shares, not the shared value, but all of the shares. And then at the end of the protocol, I'm going to check that all of my reconstruct values are consistent with everybody. So what this allows us to do is to minimize the amount of communication because I only communicate with everybody at the end of the protocol. But if I'm party 1 and I just had that previous secret sharing scheme, I only ever have to receive shares from party 4. So the amount of data that I have to receive goes down. I can ignore parties 2 and 3 from the point of view of receiving data for the majority of the protocol, and only at the very end do I have to check that parties 2 and 3 are consistent with my view to check whether party 4 was a bad guy or not. So the way we do that is we reconstruct the share vector, we hash we keep a running hash of the share vector, and only at the very end do we communicate with everybody in one big broadcast round to compare the hash value. So this allows us in practice to keep the communication down to the minimal possible communication needed, which, given that communication is going to be our bottleneck, is really important. So that's how we check Q2. So we do this running hash just like we did for Shamir last time. Okay. So that's Q2 access structures. What happens with full threshold, which is the really interesting case, because full threshold allows us to do two-party computation, yeah? Okay. So we don't have such nice properties. We don't have this Q2 property to do checking, okay? Remember, Q2 allowed us to do error detection. So we need a different way of checking. So the way we do this is we introduce what's called a global MAC key. We introduce a new MAC, a new way of sharing. Remember that every access structure has many ways of doing a linear secret sharing scheme. So we're going to create a new linear secret sharing scheme, which is going to have this secret global MAC embedded into it. And what I do is I keep I want to keep the secret the secret X that I'm sharing from everybody, from the adversary. I want to keep this MAC key secret shared, so no one understands what it is. And I'm going to keep the MAC itself also secret shared. Okay, so no one learns X unless I want them to. No one ever learns gamma, and no one ever learns alpha. Okay, so that's the kind of key. So for the initialization step is we've got to create a secret sharing of alpha. So I create a secret sharing of alpha by everyone just generating a random value in some sense. Okay, so everyone generates a random value alpha I, and then there's this secret value alpha that no one knows, which is the sum of all the alpha i's. And I'm going to call that a sharing of alpha, square bracket alpha. But my real sharing is going to be this angle bracket sharing, where I'm going to share a value x and a value alpha times x. Okay, so this is a sharing of x and a sharing of the MAC. How the alpha I are actually committed and doing things are going to be done using a somewhat homomorphic encryption scheme, which we're going to come to much, much later on. But for the moment, let's not worry about that. Okay, so we call this angle bracket sharing an authenticated sharing, because basically if square brackets is a linear secret sharing scheme, irrespective, I know on the previous slide I just done it by the complete additive secret sharing scheme, but if it is an arbitrary secret scheme, then so is the authentic. If square brackets is linear secret sharing scheme, then so is angle bracket. Okay, so we have this. The underlying matrix in the three-party case is given by this matrix here. We have this. This is the matrix of the linear secret sharing scheme, which has 2n rows and 2n minus 1 columns, and the target vector consists of n ones and n minus 1 zeros. And notice here how the matrix to generate the linear secret sharing scheme, this authenticated linear secret sharing scheme, depends on alpha. In other words, it depends on the secret, on this secret value. So no one actually knows m. So we're going to have to we're going to do operations on this linear secret sharing scheme without anyone ever learning what m is. And that's somehow what makes full threshold. One, it makes it easy because we just have to do the operations above here. But what makes it hard is the fact that the underlying matrix is itself secret. Okay, so how do we do operations on these angle bracket shares? Well, if we want to open the value x to a party, we just open the square bracket sharing of x. Remember, angle x consists of a square bracket sharing of x and a square bracket sharing of the MAC on x. So if we want to open x to all parties, we just open the square bracket sharing on x, but not the MAC, okay? But we need to check that the MAC is consistent. But we can do that, we should use the parity check matrix, yeah? I mean, that's what we did before. But the problem is, whilst there is a parity check matrix now, because we've added redundancy into the linear secret sharing scheme, which is essentially what these extra columns has done for us, we can't use the parity check matrix because it's secret. Because not only is because the underlying matrix M is secret, so the parity check matrix also depends on alpha and hence is also secret. So what we want to do is we want to have a protocol that checks the MAC is correct, the sharing of the MAC is correct, in other words that the parity check matrix is okay, but we want to do this without knowing the parity check matrix. And just like with the Q2 access structure, we did this by we checked lots of values in once by using this hash. We're actually going to do this in checking lots of values in once at once again using a trick. Okay, so this is what's called the MAC check protocol. For Q2 it's often called a hash check protocol. Here it's called a MAC check protocol because we're not checking a hash anymore, we're going to check a MAC. So we've got a bunch of values that we've opened. So suppose we've got a bunch of secret shared values in our protocol, and we've ended up opening the square bracket sharings of the alpha I. So everybody knows of the AIs. So what we want to do is we want to check that these AI values, and we've got M of them, a large number, are all consistent. So we want to check that the people, every party holds a consistent set of sharings of the max. Okay, that's it. Because if they're consistent with alpha, and you can't get a consistent sharing unless you know alpha, and no one knows alpha, so there's the only way they're going to hold a consistent sharing is if no one lied in the first place. So this is good, basically checking that you're not lying. So how are we going to do this? So it's a very, very simple protocol. What we do is we take a random, once we've got these values, we agree on a random set of these values AI. We agree on a random set of values B1 to Bm by just exchanging some seeds and then just expanding them into a random set of values B1 to Bm. The point is that no one can control these values B1 to Bm. Okay, now what we do is we locally compute the sum of Bi times AI, and we can also locally compute, because it's a linear function and square brackets is a linear secret sharing scheme, we can compute the secret sharing of the MAC on A. So we've got a value A that's public and a MAC on A, gamma, which is not public, it's secret shared. So we just have to check that gamma is the correct sharing of a MAC on A, because if this MAC is a correct sharing on A, then with overwhelming probability gamma I, the sharing of gamma I, is a consistent MAC on the value AI. Okay, so how do we do this? So we compute a linear function. Okay, so this is just another linear function. So we've now got this linear function, a sharing of omega. Now omega should be 0. Okay. So what we do is we just open the sharing of omega. And so, but the way we want to do this, we first commit to our shares of omega, and then we open them. This is to avoid a rushing adversary, because we didn't do commit and open. The person who went last, they just opened. The person who went last, if they were the cheater, they could send a value which would make omega always equal to 0. So the first they have to do is commit to what they're going to open, and then once we've got all the commitments, everyone opens, so no one has this problem of who goes first, who goes last. So, and then we just check whether omega is equal to 0, and that then is consistent. So this allows us to check m values with very, very little communication. Just agree on some random values here, and then do a commit and open, and that's fine. So this checks all the consistency without having to give away the parity check matrix. So what's summary so far? So summary, what we have is that we have this Q2 or full threshold linear secret sharing schemes can compute arbitrary linear operations for free, very fast. With a Q2 access structure, we can open to an individual player. If everyone wants to send their shares to me, I can check that all shares are consistent via the parity check matrix. If I want to open to we want to open players, we can open all the values, but only send to certain players in a qualified set, and then running the hash check to check correctness at the end of the protocol. So for full threshold, I can open to a player by opening the unauthenticated value and then using the MAC check protocol. So for the last two options, we have this MAC and hash check protocol to check consistency, and that's done in a very similar manner. So we seem to be able to now do computations. we can check computations, and we can do linear operations. Except linear operations are rather boring, and so what we really now want to do is we want to be able to compute arbitrary operations. And to compute arbitrary operations, we have to be able to multiply these secret shared values. And that's what we're going to do next. So I hope you've enjoyed this, and next time we're going to look at how do we multiply the values given this linear secret sharing scheme we've already got.